perfect opportunity for a scaling question introduced into a speed question. All right, we just determined a speed for someone on the equator going all the way around. So, all the way around in a circle, okay? Now, you guys have already figured out that we go in a smaller circle. How much smaller is our circle? Well, let's take a look. Okay, doing this quickly. Somebody on the equator goes around in a circle that's based on this R, don't they? We go around the equator, or we go around in a day based on a circle that is this big, has a radius R prime. Got that? See how it's smaller? That radius of that circle is smaller. All right, well, let's do the scaling problem first, and then we'll figure out what the scaling factor is. The scaling problem is this. We have a velocity. I'm going to use v even though it's speed, okay? We have v prime. What is our rate of speed compared to the rate of speed at the equator? Or let's do it as subscripts, make it easier to keep track of. Velocity at Langley versus the velocity of somebody at an equator, okay? So what is the velocity at the equator? Our general expression was 2 pi times the radius at the equator divided by t, which is 1 day. That's the same for both of us, right? So when we write up here, we write 2 pi r prime over t. Does that make sense? So look at everything that cancels out, and this is why we do things, we do ratios like this. When we compare things and do them as ratios, it allows us to cancel out all the stuff that doesn't matter to our comparison. Okay? 2 pi, gone. T, gone. So the ratio we're looking at is simply the ratio of our radii, isn't it? Okay? Whoever got the biggest radius is going to be going the fastest because it's in the same amount of time. Can you see that as a scaling problem? All right, so now what we have to do is figure out what the radius is. Compare the radii. All right, so velocity at Langley over velocity at the equator is going to be equal to the proportion of our radii. All right, so now let's go back up to this circle. We are at a latitude of, and that's what this is, a measurement of this angle, how far up we are from the equator, okay, from the plane of the equator. If you're standing right here at the center of Earth, this plane right here, the circle we travel on is this angle right here, okay? So this angle theta is just our latitude, okay? So our latitude is 39.95 degrees north, okay? We'll call it 40 for the sake of this problem. Okay? So now, moving along, how are we going to figure out what that is? Well, let's take a look. We'll just take a look at that part of the circle. Here's the equator. Here's Langley. And we drop a right angle right there, and we know what this theta is. What do we know? What do we know? We're trying to find this right here, aren't we? You guys understand that this is r prime right here? That's our radius, because we have a vertical line right here. It goes up through the center of Earth, so our radius is this one right here, and basically it's just a triangle. Okay, 2 upside down triangles. You got this one and this one. So that R is what we're looking for, that R prime. Okay? So if we're trying to find this R prime, do we know anything else? We know the angle, we're looking for this. What else do we know? Do we know the length of the hypotenuse? How do we know the length of the hypotenuse? It is Earth's radius, absolutely. Look, we're going from the center out to the edge. That's Earth's radius. Okay? So what we're looking for is a relationship between the adjacent leg here and the hypotenuse up here. Got that? All right, so we know this minute.
How do you know the R radius?
This is Earth's radius right here. And
How do you get your R1? How do you know that?
this R1, because we just dropped the perpendicular right here. All right? So the radius that we travel in is smaller, but it's equal to this right here. If you want to, just flip it over, and we'll call this R prime up here, but it's the same triangle. Okay? And this alternate interior angles, and then we can go based on this triangle right here. That might be easier for you to see. Okay? This triangle right here is the one we're talking about. Okay? All right, so doing that, it's easier to work with triangles when they're right side up. This angle right here we know is our latitude, 40 degrees. We know R right here because that's Earth's radius, and what we're trying to find is R prime. So we have a relationship among an angle, the adjacent leg, and and the hypotenuse, which is which trig function? Cosine. So we know that cosine theta is equal to adjacent r prime over hypotenuse r. We're trying to find r prime. R prime is equal to r cosine theta. Right? So now, going back up here to our relationship, we know r prime over r is the ratio of our velocities, right? So r prime, the ratio of our velocities at Langley to the equator, is equal to r prime over r. That's just equal to what? R cosine theta over r, cross them out. Cosine theta, the cosine of our latitude, is the relationship of our velocities. All right? We know that that number's got to be less than 1 because it's a cosine, which means that we're going to be multiplying the equator velocity times the number less than 1, which means we're going faster or slower, Brittany? Correct. Good. All right. So the ratio of our velocities, what's the cosine of 40 degrees? Cosine 0.7 something, high sixes? 0. Somebody got a calculator? 7.6? All right. So another way of expressing that is multiply side by VE. We got velocity at Langley is 0.76, or about 3/4 of the speed of the people going at the equator. Okay? So that was kind of a cool question that led right into factor label method, scaling, all the things that are going to be on this test. Wow, can you imagine if that problem was on the test?